All right, everybody. Looks like we're on track to begin, so I'm going to start. Forgive me if I sort of look a bit blinded when I look up to those of you folks at the back. There are a couple of big lights and they shine in my eyes. I should really have worn some very dark sunglasses or whatever to be able to see you at the back. Hopefully you are here to see me, Ian Cooper, talk about At Least Once. So At Least Once is really asking the question, what happens in a world where we can't use two-phase commit to talk between two databases? Who am I? I'm old. That's what most of that says. I always try and highlight the bottom point, which is, you know, I'm here only because I ended up speaking at local user groups. We didn't have anybody. And then it got me into conferences, and then that got me speaking on the stage. And I'm not smarter than any of you are. I just had the right opportunities. And you can certainly do what I'm doing, and please do think about speaking. It's great for helping you organize your thoughts and helping you work to present ideas. What are we going to talk about today? So we're going to talk about an idea called Fiefdoms from Pat Helland. Along with collaborations, another idea from Pat Helland, and Emissaries, you'll see down there at point number 4. We'll talk about where those ideas come from and how they relate to things you may have heard of more recently, because they're slightly older ideas. We'll talk a little bit about messaging, how that works in terms of what we think about as future and past, and how we do stuff in a way that's transactionally consistent. We'll come across some ideas like resources and activities. And at the end, I'll show you a little bit of some code for how we can kind of try and implement some of those ideas using an open source project I work on called Brighter. Okay. So in 2007, Pat Helland, he's an architect that's worked variously at Microsoft and Amazon. And some of the things he's responsible for include MSDTC, which is a distributed transaction coordinator in the Microsoft space. And he wrote one of the original papers that led to DynamoDB coming into existence, which influences things like Cassandra and Cosmos. So Pat's a reasonably competent fella. And Pat, essentially, his name and career had been associated with two-phase commit. And in 2007, he wrote a paper which essentially said, you know what, two-phase commit is not the right solution in distributed systems. And his point was kind of twofold, and we'll dig into a lot of it later. One is that most of us don't actually do 2PC. Most developers do something else entirely, and a little bit it's kind of recognizing the reality of our space. And quite often you didn't have a distributed transaction coordinator which worked over all the things you were trying to use. In other cases, devs just simply found other ways around it. But also, Pat was looking at a number of other ideas in this article. One of them is probably the one we'll focus on today, is service-oriented architectures, which are really a precursor to microservices. The other is he looked at some ideas for how you could create infinite scale data storage. And that's really the ideas that lead to things like Dynamo. We won't really talk about that part of the idea today, because unless you're using Dynamo or Cosmos, it's less relevant to you. And Pat also talked a little bit about the idea of saying that your application code should be scale agnostic, and we should sit over some kind of invisible platform layer that effectively deals with scaling. And a little bit, those ideas today come from serverless platforms or Kubernetes, and Pat was really a little bit ahead of his time. The other thing we'll talk about, don't worry about reading the text. It doesn't have like a magazine image I can give you, so that's just the image from Pat's blog. In 2020, Pat released another paper called Autonomous Computing. And autonomous computing is really an update of some of the ideas in life beyond distributed transactions. And it brings in some things around fiefdoms and emissaries that he hadn't really previously tied into his other work, but he had spoken about in the early noughties quite a lot at conferences, and ties that all together with his stuff on distributed transactions, etc. So this talk will cover both, because I want to basically make sure you're getting the kind of more current version of what Pat was talking about. Just out of interest for anyone who doesn't really understand what we're saying when we say two-phase commit or TPC occasionally. So if I have two databases that are essentially remote from each other, right? It could be, when we say database, it could be a cluster as well as being a database. If I want them to both participate in a transaction, so a typical example might be customer makes an order and I want to update the amount of stock we have of something on hand, right? If I want to do that across two databases, let's imagine that I have a database that serves my stock management system, be it a microservice or whatever, and a database that serves basically getting customer orders in, then effectively I'd want to take a lock in both systems. A lock effectively as I write the new order, and a lock as I decrement the amount of stock that I have of something. And the way you do that in two-phase commit is you have a coordinator, and the coordinator sends a message to both databases saying, hey, can I lock that, right? Can I lock that information? And then the individual databases vote, and they say, yep, you can do that, or no, usually somebody else has got it locked, you can't do that. And then as a result of that vote, the coordinator says, okay, we can either commit, or essentially those of you that have reserved that lock for me in anticipation of my doing something can release it. Right? And if everyone agrees, then we write the data. DTC has a performance penalty to it, as I'm sure you can imagine, right? Because effectively the coordinator has to do this kind of double questioning. So the question Pat wanted to ask, and as a person who had spent their career in two-phase commit, is what happens if we throw that away? What happens if we say that's not available to you? All right, so let's talk about Fiefdoms, one of Pat's first ideas. So a fiefdom, those pink boxes, pink hexagons, in fact, encapsulate their data. And they say, hey, nobody else can take a lock on my data. It belongs to me and to nobody else. And they have an explicit boundary. Anything outside that boundary can't reach in and take locks on the data inside that boundary. And because of that, we tend to think of the thing inside the boundary as inside data. And we expose some kind of API. We're not going to get into what that is just at this point, where effectively you can say, well, you can send me messages and I will update the state of that data inside. We also don't want to try and do some kind of join to this data over HTTP or gRPC or some other kind of RPC connection. So we don't expose what you might want to think of as a GET endpoint to just grab our data. Instead, what we do is we publish a stream of events usually, some kind of syndicated stream which gives you facts we're willing to share about data inside. And that shared stream is of what we call outside data. Outside data has some properties, right? It's immutable. In other words, it's a read-only thing that I've given you. You can't, there's no point in you changing it. The only way to change it is to send me a message on my API. I update the inside data. I issue some new outside data. And you store it, and you tend to call it reference data, right? Where essentially, because the notion is typically you're using it for reference. So for example, my current job is working for Just Eat Takeaway. We effectively service, let you order from restaurants. What we tend to do is publish the menu and restaurant details so that other services or UIs can read that data and use it to present options to you. You don't do a get from your UI to say, hey, let's get the menu from the restaurant from the service. It's particularly slow, right? If you basically put it in what we call a forward cache, you can essentially put it on CloudFront, distribute it, and get it from your phone or your web browser. Right? So we don't want to do anything that essentially says, I'm reaching in to get hold of your data, and we don't want to do gets either. There's other little fancy things on the diagram. So this set of messages that we send back and forth as we interact with a fiefdom, Pat thinks of them as a collaboration. When you hear collaboration, you should think about dialogue, conversation, or workflow. Again, we'll dig into more detail on what it is in a little bit. And that little stick figure, that's an emissary. So an emissary helps you use the API that is provided by a fiefdom. A really simple example of an emissary is a user interface. And then you can see from this diagram that while you might have originally thought, oh, fiefdom, that's just a microservice, right, Ian? The reality is a microservice is a fiefdom, but other things are fiefdoms. So the app running on your phone is a fiefdom. The app running in your user agent, your browser, is also a fiefdom, right? System which contains other fiefdoms. If you want to have boundaries that represent, for example, organizational and departmental boundaries, effectively you can invoke Conway's law and declare that a fiefdom and say there's stuff inside and stuff outside, right? This talk is less about that last option, but we're more looking at the other pieces here that we're getting into. Okay. All right. So we'll start off talking about this idea of collaborations. So I have a fiefdom, fiefdom A, it's the right-hand side as I look at it. It's the right-hand side for you too, isn't it? And I want to do some work, right? Something stimulates that work. I probably receive a request from outside. There may be a timer event. I might receive a message. And as part of that work, I'm doing some work in my domain, and I realize, I don't have responsibility for that. Somebody else does. So my typical example here is I am effectively part of the system that essentially processes purchases for us. I do some validation, I check the prices, I apply some discounts, etc. And I may have to call other services, right? I may have to call another service to figure out what are the offers that apply to this. I may have to call another service, or another fiefdom in this case, to say, well, what's the delivery fees for this? I may have to call another fiefdom and say, hey, can you take a payment for this for me? So I may not be doing all of the work, and at some point I need to call somebody else to do their part of the work. So at some point I will wait, and I will transfer control to another fiefdom. I'll say, you have control now of this workflow. And this interaction tends to result in a reply to me saying, okay, I've given you control, you go and do your work and you give me a response back. Here are the delivery fees, here is the discounts, here is the customer has paid and that is accepted, right? So this dialogue is kind of ongoing when fiefdoms talk to each other. But this is uncertain because the other fiefdom might say, our customer didn't actually manage to pay for that. Their card was declined. Right? Or we might say, hey, we don't deliver to that space. That's too far out of range. Or we might say, hey, those prices don't look right to me. I don't know where the customer got them from. Maybe somebody's trying to basically fool us by, hacking basically the front end to put in their own prices and see what happens. So there can be failures. Well, not failures, but there can be paths basically other than the happy path. And so Pat says, in a system that cannot count on distributed transactions, the management of uncertainty must be implemented in the business logic. In other words, when we don't have TPC, when we're not locking everything, we're locking delivery fees and everything else basically, what we end up doing is having these conversations, and it's our logic, it's application code that replaces TPC. And in a sense, what Pat's saying is he's recognizing that that's actually the way that most people build systems. They don't use two-phase commit. They write some code that effectively calls other code. So what does that mean if we do that, right? What it would mean if we take that approach? So some coffee shops, when you go to them, they have a cashier, and they have a barista who's going to make the coffee. And in these coffee shops, Costa Coffee, mentioning no names, What happens is that I go up and I ask to pay, order my coffee, and either, in some cases where they're understaffed, the cashier is actually the barista, goes and makes the coffee, or they talk to their friend who's the barista and they make the coffee. And essentially, I stand there waiting, blocking the whole queue, until my work is done, I get the coffee back, and I can go and sit down. And a queue will build up behind me. The constraint becomes really as fast as this barista can work, everyone will queue. And if you go into one of these coffee shops, mentioning no names, Costa Coffee, you'll see people walk out the back of the queue. Even in the United Kingdom, where, as you all know, we love queuing, and we have our own special queue, which recently appeared on television, the height of Britishness, the best queue ever. People joined it not because they liked the royal family, but because they liked the idea of joining the world's greatest queue. Even though we love queuing, obviously it gets frustrating in the morning when you're trying to get somewhere, you haven't got time to wait, etc. So you tend to give up, right? So Starbucks doesn't do that. In Starbucks, what happens, I think they actually have some kind of patent on this model or whatever. So in Starbucks, what happens, I go up to the cashier and I say, oh, can I order a coffee? And she writes basically the details of my coffee on a cup. There's an important thing, she asked me for my name. We'll come back to why that is in a little bit. And she essentially queues those cups for the barista. So basically, we just create a task queue. Same kind of thing you would do if you used a task queue pattern, right? She puts those in a queue, and the barista just comes and takes them off, services them, and gives them to the customers. So the constraint now becomes really how many baristas do we have, how many espresso machines do we have. That's about as fast as we can work, right? And then you tend to find the number depends on how much they think, the throughput's going to be in that shop. Now, I still have to wait, but generally speaking, I'm prepared to wait once I've ordered my coffee, because I can do something else, check my phone or whatever, actually, and my coffee turns up, right? But this queuing strategy is one we see a lot in software. Why do they ask for your name? Because it's a correlation ID, right? Same thing we do in messaging. I send out a request. I wait for a reply to my request. How do I know that reply, what request it was for? Generally call it a correlation ID. They don't care in Starbucks if you go in and when you say, what's your name? You say Spartacus, so that when basically they hand over a coffee for Spartacus, you can do the I'm Spartacus gag. They don't care, right? You can call yourself anything. I wouldn't try calling yourself a GUID because it's going to be hard for them to write down. But they just want to correlate messages. Exactly the same thing we do in messaging, right? By the way, if you don't know how to build this kind of thing, because sometimes they get this with APIs, if your front end wants to say, hey, I've got your order, I'm putting on a queue, it's going to go to the back end, and the back end effectively will pull them off and do the work as it needs. Here's how you do it. You basically need to rely on HTTP's 202 accepted. 202 accepted says, I've got your order, I've got your post request or whatever. I ain't going to give you an answer right now, but I got it. Which lets the UI, et cetera, go, okay, and move on with something else. What you do is in the link header, you give a URI usually to something you can poll to find out the status of your work. So you just say, okay, great, I'll poll that, and when it's done, I can essentially tell my user that effectively the work is now complete, and they can go and do whatever they need to do. Right? You can also use a push notification, so in the link header you simply say, actually you're going to get a push notification over here, sockets, that kind of thing. Right? But that way you effectively say, when I get that request in, I just put it on a queue, my web server will get to it at some point, and I'll give you back. And usually, we refer to what we call a task-oriented UI, where the user goes in, does a whole load of work to basically make selections, choose their coffee, choose the options, everything else that they need, and then they press the magic button, right? And they expect when they press the magic button to have to wait. They only want really that speed and performance when they're making selection choices. So what we do between fiefdoms is we use messaging. Okay. We don't use synchronous communication between fiefdoms, which implies holding open a transaction for a response to update multiple entities. We use messaging. Right. Overall, Pat's perspective is gRPC, HTTP, these are not the things you want to use between fiefdoms. Right? You want to use some kind of messaging solution. Now, you can tunnel messaging over, TCP, IP, HTTPs. That's not what he's talking about. But he's saying you have to send something that is kind of like, hey, I'm going to send you something. Later, you'll reply. Excuse me. Okay, so looking at my fiefdom on the right-hand side, fiefdom A, you can see that I've started some work. At some point, what happens is I need to say, okay, I need to hand over work. The work is just for application code, which is effectively guiding this particular thing that I need to do. Probably what happened is I got stimulated by a request or a message or some timer to begin some work. So the work begins, and I need to hand over to another fiefdom. At that point, I'm going to have to store some state, because I now have an operation which effectively I'm going to stop while I wait for a response from the other fiefdom, and I probably need to preserve some state to say, here's where I was, here were the state of things when basically I gave up, and then essentially send a message. I can go on in fiefdom A and do other work. Fiefdom B responds to that, picks up the message, does its work, and puts a reply back to me, and I receive the reply and I get on with the rest of my work, right? So payment you can think of, I need a payment. I suspend basically working on that order. I put it in some state. I put an enum on it for a state machine saying, hey, this order is pending payment. Save that in my database. And then effectively I send a message to another system saying, hey, can you take payment for it? Eventually it replies. I get that message in and I say, hey, I got a payment. There's a correlation ID. I will look that up. Okay, that order, I can now move along its state. So Pat talks about these things being activities. They're state machines that track incoming collaboration and a sequence of messages. This activity, which is essentially your code plus some state, can do things like, well, hey, I didn't get a response back on this one. What I'm doing is looking at things that are in the pending state, and this has been in pending state for more than a certain amount of time. Maybe I will alert an operator. Maybe I will resend that particular request. Maybe it got lost somewhere, etc. Right? So activities become the things that give you reliability. And reliability is not just simply about, hey, retry the operation that failed or something. But as I say, maybe actively monitoring these activities that you have in progress. So as a result of that, what tends to happen is that in any one of our fiefdoms, our activity tends to store this concept of, I have sent a message, I have received a message. And essentially, this message history, if you like, becomes effectively the history of our interaction with other fiefdoms via that activity in order to get work done. So each party in this dialogue, this conversation, each fiefdom essentially has a track of the conversation, although they may have a track basically as, I sent this request, I received this request, I sent this reply, I received this reply. But they're essentially tracking a conversation, and both sides effectively have a copy of it. It may be that what happens is we have quite a lot of fiefdoms involved. So in this case, fiefdom A says, hey, I need to basically get some discounts for your order, as an example, to make sure effectively that we apply the discount. So it calls basically another fiefdom that deals with promotions, and that one says, Yeah, well, effectively, in order to figure out all the promotions, I have to figure out whether this customer is on our loyalty program or our subscription program. So I'm going to call this other fiefdom that deals with that and ask it a question and say, hey, is this basically a customer on that program? It gives me a response back. I then can basically update my calculation, and then I reply back to the initial item, initial caller. So these things move across a number of fiefdoms. And so an activity can essentially initiate a new collaboration, which is, in other words, to say, rather than just simply the work I received, I'm executing it and calling one other fiefdom that requires a response to me. What I'm kicking off is actually, if you like, a sub-workflow that will complete and then come back to me, and then I can resume my workflow. Okay. So each one of those workflows is what we think of as a collaboration. And it may be that you kick off a sub-workflow in order that has to complete before you can complete yourself. Typically, we need a correlation ID, which is essentially what I mentioned with name, right? If I'm sending out requests and I'm getting responses back and they're coming in effectively asynchronously, I need to match them up and say, oh, okay, this was the response on the payment request for this order. This is the response on discounts or delivery fees for this order. Essentially, I go and retrieve that from the database, update it according to the response that I've received, and move my workflow on, right? We may also want to record some kind of conversation ID. The conversation ID will tell us there's a part of a larger collaboration. You know about the flow, this particular message exchange with this other fiefdom by correlation ID, but actually you are just one exchange in part of a larger workflow, which is basically this conversational dialogue we're having, which we also want an ID for. And that means we can track and figure out what the hell is going on at times, right? Okay. Often, that conversation may have a natural ID that makes sense. The order ID, for example, may actually be useful as the conversation ID that tells you what is happening. So these collaborations represent at least one request reply, but probably more. Okay, and it's this workflow that represents all of the interactions between fiefdoms we need to do to get work done. So we can think about the idea that this activity provides orchestration. So if you've heard the terms orchestration and choreography, orchestration is when essentially we arrange something and there is somebody in charge. They are directing the flow. And choreography is when there's no one really in charge. It's just the interactions. And we tend to often say, oh, we prefer orchestration to choreography because if I put somebody in charge, that causes a problem for me because I'm now coupled all my services to this person in charge, and essentially I can't really change anything. And quite often we worry that I end up with what's called an entity service because all of my actual business logic moves into this coordinator and doesn't actually remain in the actual domain-based microservices, or fiefdoms in our case. But what we're doing here is slightly different, right? The fiefdom's just orchestrating its individual interaction with one other partner. It's not orchestrating all interactions. Okay. And it lives basically not externally, but within the service that owns that interaction. The thing that got kicked off that says, hey, I'm the process orders fiefdom, I do processing of orders, I understand the domain of what needs to be done to process an order. I hold that logic, not an external process manager, coordinator, or something else. Okay. And that means I don't violate, say, the microservices rule of smart endpoints and dumb pipes, right? The smart, the business logic, still lives within my service. I haven't externalized it to some kind of coordinator which says, I am running the workflow. My individual fiefdom knows how to run its portion of an overall collaboration because it knows who it has to interact with, right? And each side in that dialogue or interaction has a record of the interaction through the messages that flow through it. Choreography exists here in how all of these individual conversations, these orchestrations, fit together to form a collaboration. So we still essentially get a lot of that loose coupling that choreography offers us, but we couple it with the ability for an individual fiefdom to orchestrate its interaction with a partner. So there's a dichotomy between orchestration and choreography where we think about having an orchestrator as this externalized service. There's a bit of a false dichotomy for Pat, because really what he's suggesting is that orchestration is something that an individual fiefdom does in order to interact with other fiefdoms. And it's important to try and think about why we want to do this. Often, we have causality in a workflow. There's cause and effect, right? In order to essentially take this order that you've given me and move it to fulfillment, so it gets shipped from the warehouse, cooked in the kitchen, whatever your domain is, I need to make sure that I've taken a payment. So I have cause and effect, right, in the sense that I have, from my point of view of process orders, before I move to the fulfillment step of raising a message to say to fulfillment, hey, fulfillment, you can get on with this now. Right. I need to have called the piece that says, hey, I'm going to process the payment, or I'm going to calculate the discounts, or I'm going to calculate the delivery fees. There is a sequence in which stuff needs to be done, okay? And so by orchestrating those steps from within my own fiefdom, I can make sure that causality is applied. And I don't talk about it, there's nothing on the slide here, but there's a problem space we refer to as an event chain, where people essentially throw away cause and effect and just say, I'm only going to raise events, I'm never going to send a command. And the problem is, we don't know what sequence things are happening anymore, right? And sometimes it works, and then you scale up effectively and discover, wow, I got timing issues all over the shop, and I've got things happening out of order. So this orchestration preserves cause and effect for us. And the activity can manage unhappy paths too. So if effectively someone says, hey, that payment was declined, or we couldn't calculate basically the offer, or that person has been banned as a customer, you shouldn't be offering them any service, that response comes back, then the process orders fiefdom A simply says, great, I know what to do with that. Just another flow, right? So this state machine that you're running essentially in the fiefdom is able to react to failures and then do other work. So maybe it calls an entirely different fiefdom that says, hey, I need to talk to you because there were failures in other interactions. So fiefdoms might, for example, want to perform tentative operations. This is very similar to what we saw in TPC, where essentially I say, hey, you're purchasing a ticket or you're buying some stock or whatever, and that transaction might fall through. There might be no payment, the customer might have bought before the end. So what I want you to do for me is I want to basically reserve that particular resource, right? So I say to the other fiefdom, hey, can you reserve that resource for me? Other fiefdom says, fine, that's yours, and quite often gives me a time figure. Yeah, that's yours for 10 minutes. 10 minutes time, if I don't hear back from you, I will effectively abort basically holding the reservation. You then do your work, and essentially at some point you say, hey, it's fine, that's great, I want that stock. Or you say, hey, I don't want that at all, can we abort that operation? And you can see essentially you're doing something very similar to what TPC does, but I'm just doing it from application code running in my fiefdom. I have some kind of state machine in my application code, and essentially what I say is, hey, I'm just going to send a message asking you to reserve. I get a response back. That's great. I go on with my workflow. Hey, I'm going to commit that. I want to basically purchase those tickets or buy that stock. So while this looks a lot like TPC, and it also looks a lot, for those of you familiar with it, something like the Saga pattern, it's important to recognize one of the big differences is there's no central coordinator. Application code running in the fiefdom is all that manages via the flow of messages what we need to do in order to make the whole collaboration work. Okay. Let's talk a little bit about message types. So this stuff is not from Pat. This comes from Clemens Vastas, but it's useful to the conversation to have to throw it in here. So people like Clemens have been talking about this difference between what they see as messaging and eventing. There is some argument about the terms, but just to understand basically what they mean. Messaging has intent, please buy me a coffee. Events basically provide facts, I'm thirsty. Beware passive-aggressive events. I would really like a coffee, which you send to one person with the explicit intention that they would get you a coffee. That is basically a command. You are fooling yourself. It's basically what we call a passive-aggressive event. And I'm British, so, you know. All right. So messages can do things like request and answer. They can transfer control, which is the kind of thing we've just been seeing. I send you a command, please carry out some instruction for me, and let me know when it's done. They can transfer value. Hey, I finished working on this. It's yours now. You do whatever you need, right? And generally, messaging is part of a workflow or a conversation. There is usually a dialogue involved here. Sometimes we do fire and forget. We essentially say, hey, I'm giving you an instruction, and you know what? I'm not giving you the right to refuse. I expect you to just basically do it, and maybe we'll just deal with any problems out of band, right? Customer will phone up and complain, right? By contrast, events tend to be no expectations. They're historical. They represent state that happened in that fiefdom. I'm notifying you about it, but there are usually 0 or more receivers. 0 or more is important, right? I don't know whether anyone's actually going to do anything with the fact that I'm thirsty. Maybe they'll bring me water. Maybe they'll bring me a coffee. Maybe I'll get lucky. But I don't have an expectation out there. A lot of what I'm basically shipping to you is something happened here. Often I executed a command. It may be of interest to you, and you may want to deal with that. It's how we build data lakes, and it's how we build reference data, which we'll come to in a second. Okay. It's a monologue usually, right? Not a dialogue. You are simply saying, here is some information. I am not entering into discussion with you about it. And messaging is the future, and eventing is the past. All right. So messaging says, I propose the world looks like this to somebody else. All right. Or can you make the world look like this? Can you take a payment for me? Right. Can you apply discounts? Can you apply offers? Only a fiefdom has a notion of now for things that it owns. As soon as data leaves the fiefdom, it becomes effectively stale, right? Because essentially it can only represent what it knew at the time that it gave you a response or issued an event. So if we want to update something and say, hey, future people, what does this look like? I have to send it basically to another fiefdom and say, please update it based on your context of now and tell me what happened. So jobs, work, that kind of thing where I have an expectation that you do it, tend to be done by commands. Right? And it's these that you see a lot of activities dealing with. Events are past states. So when I get a response back, it will be an event of some sort, right? Because it represents past state. Hey, a payment was made. That happened. It's not happening now, right? And we have to be aware of that past state because essentially sometimes it may no longer be accurate, right? Here is basically the customer's address in case you need it in the future, but the customer may have gone and updated that just moments after I gave you that information. You're hoping I will send you another event later which will update you so that you can catch up. All right. And so when I receive a reply as one of these basically activities, it's generally an event I'm receiving. Events tend to come in 2 forms, serious and discrete. So discrete ones say, oh, hey, you know what? Here's an event. I'm sending it to you. You didn't really ask me for it. Please, can you react to it? And serious events basically say, hey, I'd like to ask you for information about this. So it's how we do queries instead of doing get, right? Discrete, continuous. Discrete, basically, effectively, there's just one of them. You handle that. You're not looking for others. Continuous, I'm subscribed to it, and it will keep sending me more updates. It's syndicated. Independent, in other words, effectively, I deal with this one, doesn't bear any relation to the others. This reply is the reply to that request, to the request to make a payment. It's not a reply to other requests to make, it's not related to other requests to make payment. Sequential, this represents some data like changes to a customer account, and you'll want to keep listening to it because you want to get all the changes, and they're related to each other. Immediately actionable, generally you receive a reply and you expect it to do something, right? Hey, the payment was updated, I'm going to advance the workflow. Or for series, basically condition or context. So it's saying, hey, this is the state right now of the customer, you may need that information in the future. And discrete is part of the conversation, it's a reply. Usually, and series effectively is part of a monologue. It's essentially that service telling me stuff, but it's not expecting a reply or response from me. So to go back to this idea of reference data that we were looking at earlier, reference data is when essentially I say, here are some facts about the data I hold you may want in the future. You may want to have the product catalog so that you can make orders, right? We ship you menus. We do that by effectively putting them in an S3 bucket and publishing them in CloudFront so you can pick them up from your web app or your phone so that you can effectively then, the customers can make orders, right? You don't do a get and ask us for it. We publish it to you ahead of time, right? And reference data is a really important part of how we tend to scale in event-driven architectures. It says, don't do gets to other services because that introduces temporal coupling and synchronous conversations. Subscribe to a stream of data from them which you can store locally, and you just look up in your local, what's often called a forward cache of that data when you need it. So you don't do gets anymore, right? And this is all part of this idea of your data living inside your fiefdom is not available to me, but outside data is available to me. Okay. All right. This is basically a monologue. Pat sometimes calls it a syndication, right? His example effectively is the old school, Sears catalog that would drop 2 or 3 people's letterboxes and then they could effectively make orders from them. That's effectively what this reference data is. All right. Emissaries. Emissaries are essentially the way we interact with fiefdoms, and the simple way of thinking about an emissary is basically a UI, though it could be an SDK. Typically, this is the way you begin to realize that a fiefdom, as well as being a microservice, could also be basically a user agent or a phone app, right? And essentially, quite often, it's using the reference data to make selections, and from those selections, it makes requests basically to the fiefdom for action. Fiefdoms don't trust their emissaries, they validate the data that comes through them. All right. The way to think about this often best in order to basically make this work is to conceptually believe that your emissary is always offline. And by that we mean you should provide your emissary with the data it needs to do its work, and when effectively at the end you need to basically have action from the fiefdom, you hit kind of a button and you send it to the back end, you queue it for being sent to the back end. So even when you're, for example, taking an order from a customer on an e-commerce site, you give them all the data they need to basically build up the order, or the product catalog information, all the data they need, they build up the order, and the point where effectively they hit the button, you can pretend kind of up to then you're all offline, and essentially that's the only point you need to communicate when you effectively then say, I'm going to send something to the back end to actually get work done. All right. So we said, hey, we don't use synchronous communication between these fiefdoms. We use messaging. So it's an important thing to understand is that if I send a message to represent some change in state, I've updated my local activity, and I now have said basically we are now in the payment pending status, it would imply that I've also sent a message which says, hey, please can you take the payment? And the problem is, if I live in a world without two-phase commit, and it's quite likely that between a database and, say, a message broker, I wouldn't have a coordinator because they come from different vendors anyway, there's a real danger that essentially I would update basically the data and move it to payment pending, but the message doesn't get sent. So it's important when we do this to have transactional messaging, by which we mean that the message must be guaranteed to be sent if we change the state locally. The typical way to do that is called the Outbox pattern. So in the Outbox pattern, what we do is we create another table that basically says, hey, we're going to set the messages in here that we're going to send. And then in a transaction, We can write basically a transaction that both makes the change to our activity, we'll figure out what resources are later, but resource as well, right? And at the same time create the message that goes alongside them. And then we simply poll that outbox table by a worker process or thread for anything that hasn't been sent yet, and we send it. And then we mark it as sent when the broker tells us it's done. All right. And that effectively means that we guarantee that our messages that are outgoing represent our internal state. And in a sense, this is basically part of what an activity is doing. It's recording outgoing messages. We don't know whether or not effectively the failure for a broker to acknowledge that the message was sent comes because it didn't actually send the message or we didn't receive the acknowledgement. We can't ever really know that. It could just be a network connection on a failure on the response. It could be that the broker effectively just timed out doing it, but effectively in the end replicates it all around its cluster, and the asynchronous response we get says it failed, but we already succeeded. And so the risk there effectively is that we end up, because we don't mark basically that item as sent in our message box from our worker thread or process, sending it twice. Right? You didn't respond to me to say the message was sent within a certain time frame. Effectively, I look at my track of unsent messages and I say, well, this message has been sitting here in my outbox table marked as unsent for too long. I better resend it. It may be that eventually the broker's going to respond and tell me, yeah, it was sent, but I can't take that risk. I need to resend it because I've got timing of the whole operation at stake here. And that means that you should expect duplicates. And because you should expect duplicates, you need to have some way of saying, I need to deal with that problem. Now, you could just be idempotent, in which case effectively reapplying that change doesn't matter. And that's more typical with events. But with commands that are requests for work, it's often difficult to do it twice. So we create a thing called an inbox. And we say, I'm going to record all the messages I've received. And then what I'll do is just look up and see whether I've received that message already. And if I have, I don't need to action it. So remember, activities not only do messages we have sent, but they also do messages we receive. The other alternative is idempotence, right? There are no substantive side effects. You can just ignore the fact that you need to do the inbox. So sometimes, for example, if I receive a reply saying payment was made for an order, I don't necessarily need to worry about checking that in an inbox, because if I reapply the order was paid for, well, the order was still paid for. We may also need to reissue our response if we get a repeat message. If we get something that comes into our inbox says, can you do this again? We don't necessarily know whether that might have been a deliberate resend because something downstream from us has failed, so we quite often have to have the capability in our inbox to say, actually, you know what, you should resend the message that you had before. Typically, if you have an outbox, you can just clear the published value on the outbox, and then it'll just get resent. And it has to be effectively the same response we created earlier, so the outbox helps you out there, right? So the outbox pattern depends upon you being able to have a transaction in your database. What happens if you can't have a transaction in your database because you don't have, using a document store or something that doesn't support transactions across multiple tables or multiple documents? A couple of other options. First option is log tailing. Typically, your database may expose effectively writes as a stream. You listen to that stream. When you see a write, you take the action of creating the appropriate outgoing message, write that to the outbox, and then your worker process just reads the outbox from there, right? So it's kind of an extra step where effectively you're saying, because I can't have transactions, I'll rely on being able to read the stream in order, and then I'll just write the corresponding message to the outbox, and then that will get sent. A little more delay, but it works without transactions. The other option you have is basically to send the message and listen to your own message and update your state when you see your own outgoing message, right? It's simple, it's effective. The only slight thing is timing, right? If somebody else wants to ask you what the state is, you may disagree with somebody else downstream who's processed the message before you have. So just be wary about timing issues if you choose that option. All right. Okay. So our overall model inside some kind of fiefdom looks a bit like this. I've got some kind of collaboration I'm participating in. The collaboration doesn't exist as anything probably more than IDs for a conversation or natural IDs that I'm attaching to messages. It may also exist in some kind of span that I'm putting into my telemetry. And I am receiving messages into my fiefdom. Some of them are initiating work. Some of them are during basically the process of some initiate collaboration. Some of them are steps in a collaboration. And that runs application code. Remember, Pat's point is it's application code that has to deal with uncertainty in the absence of basically TPC. And it will effectively update a couple of things, what Pat calls resources. Those are abstractions over things, right? And activities, which essentially are notions of state, and the state basically that a given activity that you own, which is a portion of a workflow, is in. There are multiple ways to implement this. As Pat points out, it's application code, so there are lots of options for us, right? Things like aggregates, obviously, if you know DDD, have a strong affinity for this because they are essentially state machines over some resources. But you could even use a workflow engine inside your fiefdom, right? You could just have a notion of an activity and a resource as being quite explicit concepts in your domain. There is not effectively a prescribed way of doing this. The important thing to understand is that you have individual fiefdoms that have activities, that have code and some state that run their portion of a collaboration, and you don't have a centralized controller running it. All right. So we'll briefly look at Brighter. So Brighter is an open source project that I work on. It's for .NET developers. There are equivalents, I think, like mass transit and service bus, rebus in RSpace. Outside RSpace, if you're a JavaScript developer, I recommend going to look at Seneca. If you're a Java developer, you're probably just embedded in Spring anyway, so what does it matter? But there are various alternatives, right? We'll just show you how this one works so you get a feel for it. So this hideous diagram represents basically how Brighter works in terms of receiving messages. There's a dispatcher at the top. That's basically a supervisor worker that says, hey, I'm going to spin up some threads, and something needs to own them all. For any given subscription to messages, so someone who's saying, hey, any messages basically on this topic or this routing key, I want those, we have a consumer. And a consumer can spin up any number of threads, and we call them a performer, which essentially will process messages from that given subscription. So if it's a queue, from that given queue. If it's a stream, effectively from that given stream. Generally, if it's a stream like Kafka, you only really want one performer, but you can do competing consumers and multiple performers. Right? And each performer has a message pump. And the message pump says, my job is to go and read from the message queue, and I get a message off the queue, right? And I turn what is the JSON or Avro or protobuf body into something you can recognize in code, so a type in your type system. Then we give it to what we call a command processor, and that says, okay, find some code that handles this message. And it runs a middleware pipeline. And that middleware pipeline does a number of things. They're optional. So one of them we do is an inbox, which says, have I seen this message already? If I have, I don't have to process it. Other one is basically for .NET devs is Poly. We basically offer you resilience there. You're not a .NET dev. That's just stuff that does retries and circuit breakers. And you can add your own middleware into Brighter basically to do steps that you want, right? And then finally, you've got your request handler that runs your domain code. Okay. This portion is essentially what an activity does. There's an inbox to check for stuff. There's some domain code that you can run. We also offer you an outbox. So when your request handler wants to basically write an outgoing message at the same time as updating resources that it owns, we can get our outbox to participate in that transaction. such that effectively we will write messages to our outbox at the same time as you update your resources. And we also offer you a sweeper thread which will go through and look in your outbox for things that haven't been sent and try and dispatch them to your broker. Okay. What does it look like? This is the only bit probably for the .NET developers. The rest of you can kind of just glaze over if you like. So we basically use attributes for middleware pipeline, and this one is saying, hey, I need an inbox. I want to deduplicate stuff. I don't want to basically try and rely on idempotency here. Then we have a handler. So if you're dealing with fiefdoms that deal with messaging and activities, in a lot of cases what happens, you have this kind of model where you have a handler that says, I am reacting to being sent a message. I am either initiating basically my part of a collaboration, my activity, or effectively I am responding to a reply as part of it. We'll see a reply in a second. Then we begin a transaction. We support a number of common tools in the .NET space, Entity Framework Core, this is Dapper we're using here. So we begin a transaction explicitly because we want to participate as part of that transaction in order to write to the outbox. Then in this example, we're using some kind of aggregate-based approach. So the aggregate contains a state machine and can take our order through the various states involved. So here we go to a factory and say, well, we're creating a new one. It's the initiation of a collaboration. So we use a factory and we create our new order. And we check basically from the checkout information we've received as a message that wants to initiate the order process. So I forgot to mention that we've listened to a checkout event. So we want to create the order based on the customer's checkout. We're going to process it and take payments for it and stuff like that. We want to validate it's correct, and then we'll save it in the database. And then we create basically a message for payment. We're not done on process order until basically at least we've got it paid for. Well, then we'll hand it to fulfillment, right? So we create an outgoing message, and we say, we want to take a payment for this, and we write it to Postbox. So Postbox is just our command processor. It's just a local name in this code for it, right? And we say, put it in there. So the Postbox notion is just basically, hey, here's someone who wants to store something. And then we either commit the transaction, and your new order exists in our data table along with the request to pay for it, or we abort the transaction, and neither happens, right? So later on, in the same collaboration, well, the same activity for us, we might receive a response back from the payment system. Again, there's an inbox, in case you've seen it before. We might have been okay with not having an inbox in this case because, payment is payment. But we do ship to fulfillment later, so probably we might want to do that twice. We listen to the payment request, right? This handler gets kicked off when a payment request comes in. It just runs your handler code. We look at the payment request and we say, let's begin a transaction. Let's find essentially the order this payment relates to. The correlation ID is going to just be the order ID. That's what we're using. We can use the natural one. This is just some Dapper code for those that don't know .NET or haven't seen it. And it's saying, go away and find me the order that matches this order ID. I want to get it out. And then I'm going to call a method on it to essentially advance its state by telling it a payment's been made. And then I pass in the payment details to it so it can update whatever it needs to update locally, presumably the order resource. And then I want to hand this work on to the next step. And actually, usually, the fulfillment will be a different fiefdom. So I'm going to send it a message to begin a collaboration for fiefdom to do that work. So I create a fulfillment request, and I put a message in my outbox saying, hey, go and do the work basically in order to fulfill this, right? And then again, I commit or roll back the transaction. None of this has required me to build an external Saga process manager coordinator. Just so you know, this is kind of how you configure Brighter such that you would get an outbox. We support a range of databases. Effectively, what you're doing is saying, hey, I want to use this type of outbox, and here's some configuration information for it. This line says, hey, you should use, we need to share these transactions when you're writing basically the outbox. And this line says, I want to use a sweeper. So I want you to basically spin up a thread that will monitor the outbox and send messages basically that haven't been sent yet. Sometimes You don't want to wait for the sweeper to run. You don't want that kind of delay. And you just want to say, I'm going to try, first of all, to send it immediately. The sweeper's just going to basically try and send stuff that didn't work. And that's OK. What you can do effectively is create a list of posts, add your post effectively into the list of posts, and you can explicitly just clear it all at the end of your handler. Right? So, just to kind of summarize, Pat's argument is that application code is what you use in distributed applications when you want to replace TPC, not something like a Saga or process manager, etc. Now, the application code that does that orchestration runs in each individual fiefdom. Fiefdom could be a microservice, but it might also be code running basically on a phone or a user agent or a browser. And what we do is essentially write activities. And activities effectively are code that handles the workflow portion that I need in response to a message. And it may pause because it starts its own collaboration saying, hey, go and do this other work for me, and receives a response back and wakes up. We wake up the state for it and then resume it. Right? And the combination of all these activities running, which is effectively choreography, forms a collaboration we can use. Don't need to use TPC, don't need to use a coordinator or a Saga. And your code to do that is something like this. All right? Some kind of handler with some middleware to deal with things like outboxes and inboxes, etc., that you need. All right. That's that talk. It's traditional to put the green ticket in the box outside when you go. Thank you very much.